There we go. Okay. Hi, everyone. So one of the things that we like to do, we've been practicing doing a little bit of annotating. And so let's bring up a screen just for the fun of it. And so today we're kind of looking at the solar system a little bit. And so here's some scenes from one of the objects in our solar system from some movies. And so there's a lot of different ways that Mars has been portrayed. And so, you know, maybe you're familiar with these. Which one of these movies do you most identify with, or how did you most enjoy? Or which one are you currently identifying with the most? This might be a good question. So.
Brian, is the lower right one that just says Mars, is that actually Mars, or is that a movie? Is there a movie named Mars?
No, there's not. That they superimposed a person on that. That's an actual image in realistic color from, I believe, the Curiosity rover. And so the other ones, it just kind of points out that there's been a variety of different ways in which Mars, as well as other solar system objects, have been portrayed in the media, popular media throughout history. I actually have a whole program on that, which is, maybe we'll have to do that one of these days.
And can I just check in to see if people know where the annotation button is? If you go up top to the view options, there's a little caret or arrow right next to the view options, and you scroll down, you'll see a button that says annotate. And if you click on that, it's going to bring up a bunch of different options. The one that I was using is this stamp for the heart. And I see someone else is doing that too now. Someone selected Space Odyssey.
Yeah, thank you for jumping in on that. I appreciate that. I forgot to note where to find it.
And now I see a stars going on. So good.
Yeah.
So people are finding it. Great.
So let's clear those for now. We'll have a chance to come back and practice that again here shortly. So what we're going to do is we'll kind of go quickly here. And so what we want to do is we want to think a little bit about observing phenomenon. This is something that a lot of schools, and actually because of the new standards, that students interacting and collecting evidence and making evidence-based explanations of natural phenomena. So the next slide is going to show an image from the surface of a mystery planet. And so what I want you to do is to make some observations of the phenomena in the image, use your annotation menu that you just used, put your observations up in the image. If you agree with somebody's observation, put a check mark or a star next to it. And so this will give us a chance to kind of make some observations of some things that are going on the surface of a mystery planet. So here we go. So annotate away. I see a star. I don't know what that means. And so try to make observations, and you can actually, there's a text tool that you can use the text tool to write in what it is that you're observing. For example, you could put down here that this expanse is blue. And you could change the color of that as well. I think I spelled whitish right. All right, so we've got a few observations there. And so what we want to do is we're going to leave those there just for a moment. And let's see if I can, maybe I need to get out of that. So how many of the observations were actually inferences? And so let's go back there. And so how many of these observations that you made are actually inferences? And since there's a relatively small group, feel free to unmute yourself and go ahead and tell us.
Well, I was the person who noted the building, and I was going to say a man-made structure, and then I said human building because it's something that is human-based, but I don't. But it could be built by anything. We don't know that it's human. So then I tried to erase it, and I couldn't change it into something that. As I was thinking maybe it's a natural, a non-natural structure, I might call it.
Yeah, and so, I tried not to call the clouds clouds, but I think I went a little too technical by calling them condensation in the atmosphere. I guess it just looks like that, but again, it's an inference based on my experience of clouds being made of particles of liquid. So maybe it's something completely different that just looks like that.
So, yeah, so if we look at this, and so we have somebody said that there's snow-capped mountains. And so we look at this and, most of us would agree that, yeah, we look up and we see snow-capped mountain. Well, what is it that makes it a snow-capped mountain? What observations do we make that lead us to the conclusion that what we're observing are snow-capped mountains? There's some observing and some patterns that we're used to seeing that lead us to the conclusion that there's snow-capped mountains. What appears to be organic life? Here's another one. And so we have these patterns that we're used to making observations of. And so we come to the inference that there's organic life, saying that they're mountains. Mountains would be making an inference based on some observations of some, apparent differences in elevation within this scene. It's a valley. Well, what's a valley? What is it that makes a valley? How do we define what these things are? And so when we go to try to explain what's going on other worlds that we're not familiar with, sometimes we need to kind of take a step back and think about the different phenomena that we're experiencing and the ways in which we're describing them, and to really kind of stop and question whether or not we're doing this from a making inferences or whether we're really making observations. Okay, so let's move on here. So it really helps to be able to think about the definition of these things. And so if we define what we mean by observations and inferences, observations basically descriptive statements about natural phenomena. And I need to move this, all of you are getting in the way. There we go, I can actually see what we're doing. So descriptive statements about natural phenomena, you can read this. And the thing about observations is that usually people can come to some sort of consensus about what we're observing. Inference is a little bit different. We can't always come to a consensus about the interpretations of what we do with our observations. And so the inferences are interpretations of what it is that we're observing, hopefully based on the evidence that we're making, that we're observing. So one of the things, if you're familiar with the next generation science standards, and if we're thinking about what we're asking students to do within our classrooms, and a lot of times it helps to be able to kind of lump the science practices together into some different categories. And if you think about it, and a lot of people, when they look at the science practices, they kind of scratch their heads and say, well, gee, you know, these things are kind of related. How are they related to each other? And so if we think about what the students are actually doing,
Ryan.
the student behavior. Yes, ma'am.
Oh, sorry, I just couldn't hear you for a minute, but looks like everybody else could. Sorry.
Oh, okay. Okay. So we kind of think that there are some basic behaviors that some of these practices kind of fit themselves into. Students gather evidence. And so there are some practices that have to do with their gathering of evidence. And then modeling is actually something that crosses over all these. You can actually use a model to gather data about phenomena that you're modeling and then see how your model behaves and then go look at the actual natural world to see whether or not it matches up with the model. There's reasoning about the evidence that they gather, and then there's communicating the information or the evidence that they've accumulated. We can also think about the crosscutting concepts and how those work, and all of these, there's some kind of categories that we can kind of think about these. And so there's three: scale and proportion, change and stability, matter and energy. In a lot of ways, this has to do with properties of systems. Cause and effect, structure and function, in a lot of ways, are properties of causality. And then you have patterns that go on to help you to be able to define those things. And so if you think about the phenomena that we're trying to investigate, then all of these things work together. Students are using, and scientists in general, really are kind of finding and using patterns as evidence to determine cause and effect relationship within the systems that are being investigated. And this all brings to bear on the phenomena that they can directly observe within the classroom. And so here's a nice phenomena that a lot of students have wanted to look at. Back in the late 1970s, the Viking orbiter, it had the orbiter, but it also had the lander, took some images and sent these back. And some people looked at this and said, oh my gosh, look at that. We've got evidence of what? What is that? What do we have evidence here, supposedly?
It's the Mars face.
It's the Mars face. And so there we've got, oh, that was supposed to be let me make it do that. There we go. It's the face on Mars. And so this is kind of an interesting thing. You know, people jump to this inference, they have this observation, and of course, there has to be people or someone on Mars that's intelligent and sending us a signal that hey, those humans on Earth are way cooler than we are, and so we're going to put something up to kind of recognize that. So later on, they went up with some other. Why is this doing this? I've just discovered something. When you're in annotate mode, it won't let you advance. So they took some other images. Here's another one with a little bit different, little higher resolution, similar sort of shadow patterns. And with the higher resolution, the face kind of disappears. Under a different angle with the sun, the face kind of disappears. Looking at it from an oblique view, you know, there's not a whole lot of facial things there. And so sometimes you have to be able to look at things a little bit differently. And if you see something and make this claim, and Carl Sagan said it best, that extraordinary claims require extraordinary evidence. And so if something just seems too good to be true, a face on Mars, let's keep looking at it and see if it remains consistent throughout other different conditions. And so, but this kind of went right along with this idea that once upon a time, we figured that, oh yeah, there had to be, you know, some intelligent beings on Mars. Now it turns out that no, it's just a misinterpretation or a hopeful interpretation of the actual phenomena that they were observing on the surface of Mars. So this is kind of one of the things when we're looking at the solar system that we kind of confront this and not try to leap to these conclusions. You know, we want to think that, oh yeah, there's a subsurface ocean on Europa, and so there must be life there. Not necessarily. What evidence is there? How can we go about collecting evidence? And so here's kind of another example. And so if we think about this, and how are we doing on time? I don't want to take up too much here.
We had budgeted you for about 30 minutes and you actually have only done 16. So
16, 1-6, okay. So here's one, let's kind of, you know, here's a scene. Looking now, what kind of things could we observe here? And go ahead and use your annotation buttons again and write in some observations. And if you want to make some inferences about what's going on in here, feel free to do that as well. And so observations and inferences are fair game on this. So go ahead and make some using your annotation bar. I see an arrow. Whoops. I see that kind of smooth areas, light. So this is one of the things that we, most apparent clouds, okay, landmass. And so if you say landmass, what, okay, perhaps water. So we're making some inferences that are going on here. And so we could make the inference here that these white kind of poofy things might be clouds. Someone said clouds. And one of the things that's interesting is that if you look at one of them, can you see my arrow or can you see my arrow? Is it moving there? Maybe not. Let me find my annotation button. I don't know where it went. There it is.
yeah, you might have to click on mouse, but I see it moving.
Yeah, we see your cursor.
Okay. So one of the things that you could do is if you look at this right there, and so I put a little red, little blue arrow here, you notice that here's a white blob, but right next to it is a similar size or similar shaped black area. And if you look here, that all of these white things have these little darker areas. And so you could say, oh yeah, clouds and shadows of clouds. Down here, you could use a different color. So down here, you could think, oh, it didn't change the color. How about that? And so down here, you've got maybe a beach strand. This out here is very uniform. Maybe it's water. This is dark. And so some of you might recognize that this is Los Angeles, and this is from a satellite photo. We've got cloud banks, we've got land, we've got water. And so when we look at this, again, we go back to thinking about what do we know and how do we use what we know to interpret what's going on elsewhere. And so here's something. If you're think about this, are there any similarities that this has to that? What sorts of similarities do you see?
I think, did you want us to unmute or put it in the
Yeah,
chat
you can
or
unmute.
annotate? Because
Yeah, I put my, I
white
closed
stuff
my chat so I can't see the chat.
looks like snow. You
Or
know,
if you
we're
think of the last,
extrapolating or clouds.
well, if you think of the last image and you think of what we said was water, this water out here, was there much of a pattern to the water?
It's dark.
It's dark, it's uniform, the land surface is more mottled. And then if we look here, the darker area, there's less definition in it. These lighter areas have more definition. And so maybe we could infer that, oh, look, we've got some sort of a liquid, some sort of a land type thing. And then we stop and pause and think, well, where is this? It turns out that this is on Titan, which is a moon of Saturn. And so the inference is that there are lakes and land areas. But then we realize that it's really, really cold there. And it's, well, let's see, the lakes must not be made of water. It must be something else. And so what are they possibly made of? And so now we have, based on these inferences, based on what our prior experience is with other bodies, with what we know on Earth, then we can extrapolate these ideas to perhaps some of the processes that are going on elsewhere. You go and you pick up a rock, and you see these this pattern of this interesting kind of pattern to these polygons. Well, that's kind of an interesting pattern. And you think, well, there's some rocks. These rocks are supposedly 1 billion years old. So, what's going on here? What was making these little marks? And so you go for a hike someplace else and you see this sort of thing. And then you realize, oh, you're out at the beach or you're at an estuary and you're on a mud flat. And you see this and you say, wow, that kind of looks like those rocks that I was looking at. So I wonder if these rocks are fossil evidence of a mud flat, which is kind of an interesting thing to think about. I think that these are rocks from Montana. And then furthermore, you end up seeing a picture that looks like this, and you notice that, oh my gosh, there's some real similarities between that and this and this. And then you think, well, gee, that's on Mars. So maybe we've got a little bit of evidence here that maybe there was some sort of process similar to this going on Mars. This was on Earth. This was on Earth many, many years ago. And now you've got a similar sort of process that perhaps took place on Mars. So yet another piece of evidence or inferential evidence that some liquid water was present on Mars. And so these are the sorts of things that scientists and planetary scientists use when they study other objects within the solar system. Another one, if you go down to the beach and dug a hole in the beach, you might notice all these nice striations and how they change directions. And then you see something like this and you realize, oh, we've got these little striations. They seem to change directions, kind of like this. Only this is again on Mars. And so then you come to the conclusion, oh yeah, there must have been some sort of a process that was creating these dune-like structures or beach-like structures on Mars, because we see a similar sort of, I guess, morphology of the layers and the rocks. And so these are some of the things that we use to think about the different processes that are going on elsewhere. Also, if we look at this, if we find a place with rounded pebbles on Earth, we might think, oh, how do you make rounded pebbles? What do you have to make rounded pebbles? Where would you go to find round pebbles?
Flowing water.
Yeah, flowing water. Maybe at the beach, maybe in the rivers. And then you realize, oh, one of these is on Mars, the other one's on Earth. And so again, we have a piece of evidence, inferential evidence, to suggest that once upon a time there was water on Mars. Evidence from satellite photos, we have these analogous structures that we can see. And so we make an inference that there was a delta structure on Mars, and with a very similar look to an existing delta that flows into Lake Baikal in Russia, and similar sort of distance scale on it as well. Well, things aren't always easy when it comes to thinking about what things are, or even what to name things. And so here's a body in the solar system that asks itself the question, what am I? Am I suffering from an identity crisis? Do I just have an inferiority complex? Or am I just plain misunderstood? So this is something that, you might recognize what object is. Who knows what object that is?
Pluto.
It's Pluto.
Pluto.
So Pluto has gone through this thing of, what do we call Pluto? What is Pluto? So on the next slide, what we're going to do is we're going to note the properties of a variety of solar system objects. We're going to organize them in groups based on the properties that are provided. And we can use our annotation tools to indicate which objects we think belong together into groups and the property which is most important for determining membership of the group. This is just a very small segment of this. The normal one, if we were in person, we would probably spend 2 hours doing this, and you would have a great many more objects to categorize this. But because of a space and time limitation, I'm only giving you 6 or 8 objects, I think 8 objects. And so what we want to do is we want to think about the groups that these go into. And so I'm going to have to stop share and go to the other. Where'd it go? There it is. Okay, so here we've got 8 objects. So using, and you don't always have pictures for these. And so this is the way, if we imagine that we're somebody back in the 18th century, we're talking the 1700s. This is what was known in the 1700s. How would you organize what we call things in kind of a pre-industrial age, you might say, back when science was in its very beginnings? Which objects would we put together? Some interesting properties. So use your annotation tool and you can draw some lines between some things and make connections between things that you think might belong together. Okay, so we're indicating that a whole bunch of things orbit 18. We don't know what it's orbiting. All right, and so now we've got this idea. We're going to leave these here. And now what we want to do is we want to move into more of the modern age. And as we've gotten better at understanding things, our technology's gotten better, our ability to investigate these solar system objects gets better. And so now we know a little bit more about them. We even have some imagery. So let's think about the groupings that you had there. And so what we end up doing is there's a second phase to this, that we give people a second set of cards that don't replace the existing cards. They just give us additional information. And so then we think about, oh, what does this do to the groups or how we categorize these objects within the solar system? And so think about how you categorize things before, and now you want to think about any changes that you might want to make to your groupings. And I think it's interesting that object 10 and object 18 appear to be made of the same thing. And as does number 17. And so we've got some similarities there. And so you have to think about which properties of these are the most important as far as determining what kind of groups they belong in. Okay, we've got some rocky objects that are being noted. And we're probably about out of time, right, Teresa?
Yeah, This
Okay,
is
so we're
very
almost done
interesting.
here. And so now what we do is we go even further into the modern times with even more, with the same objects. And now we take a look at better imagery, better data, and we think about whether or not the groupings that we had come up with are still applicable, or whether we want to modify any of the groupings that we have about these objects. Maybe we need to add groups, maybe we need to subtract groups, maybe we need to lump them together, but we're constantly going through and refining how we call things. And so the last thing that I want to show you is that there are some outliers. And so down here, object number 26, down here at the bottom, one of the things that's interesting, it's made out of rock and ice. It has a tail. Tails are usually associated with things that are mainly ices and gases, comets. And, and we haven't called these things anything yet. And so here we have something that's primarily rock, and then it has a tail. Is it a comet based on the fact that it has a tail, or is it an asteroid based on the fact that it's dominantly rock? And then it turns out that many other asteroids also have ices, but like 15 here, it has some ices in it, but we typically, there's not a whole lot of argument about whether or not we call it an asteroid instead of a comet. So there's some objects that don't quite fit neatly into our, whatever our categorization scheme that we have is. So this is kind of a fun activity to do. There is a set of cards, kind of the basic activity. There's a set of cards that you can get with some descriptions on them. And then there's an image on the back. And I'm going to put where you can find this in the chat on the Night Sky Network website. And it's freely downloadable. And so you can find a slightly different version of the same activity there. All right. Well, I didn't go over too far.
No, I think you did great. And I just was wondering, is the observation inference thing in the solar system cards activity as well?
No, they are not. That was something that we added, and that's something that is very easily done. All you have to do is you can take basically almost any picture and put it up, as long as you put something up that almost everyone goes through and makes inferences when they think they're just making observations. And so I kind of like to think of it as a little game that we play, this reductionist game of how far back do you go until you get to a point at which you start not being sure of what the observation is that makes something. What makes it a snowy mountain? How do you know it's snow? How do you know that it's a mountain? What's the indication that it might be snow? At what point did little kids learn all the different things for them to call things? At some point in our young lives, we learned these specific observations that were associated with certain things. And so what we have to do is we kind of have to imagine ourselves as a blank slate of not knowing what it is that we call these things. We have to kind of make believe that we don't know what things are called to truly get down to what the real observations are. So.
Very cool. Well, thank you guys for that, Brian. I really like this idea of investigating the solar system with the observations, and I'm kind of taking a little bit of a different tactic about science observations, because when you are dealing with middle schoolers, one of the key things that they're doing is starting to question their identity, and having a science identity has been seen to be something that can carry through your whole life or can change at any time. So it's a new, a lot of research is going into what makes a science identity. And so I have something that is sort of a question for everybody, and we can use the annotate tool again. But let me share my screen and I can ask you this question. And it's actually written on the slide. But if you can use the annotate tool, just mark which one is an astronomer of these people. So you have to pick which one you think is an astronomer. And also the annotate tools, unless you use the arrow, I can't see who's picking who. So I see there's somebody who picked the person in the upper corner. Some people pick the other corner. Somebody is gold starring all of them. Yes, so that is the take home of this, is that all of these people are astronomers. And the reason why I wanted to start with this is just because a lot of times in our heads, even after we go through a lot of professional development and such, we still have ideas of what an astronomer looks like and what a scientist looks like. And so all these people are astronomers, and it's this is an activity where this is a draft version of it, but we're trying to get the idea out into the world that astronomers can look like anyone, especially people who might not have that idea because they're underrepresented groups. So that's kind of what I wanted to talk about, is sort of this idea of science identity and the idea of growth and fixed mindsets. Raise your hand if you've been already through a professional development about growth mindset. Yeah, so people at ASP, yes. But so this is the idea that's come about in research and education over the last, I would say since the 80s, so almost 40 years now, when you might have heard phrases like, "You're so smart," or "Wow, you're really a natural, you make amazing paintings," or "You're so talented," or those are some positive phrases. Of course, there's not so positive phrases like, "Oh yeah, this isn't your thing," or "You aren't a math person," or those are kind of phrases that people hear that is really a reflection of a fixed mindset. And what a mindset is just these attitudes that we have, that we believe, sometimes consciously, sometimes subconsciously. Just they're the attitudes that we grow with. And a fixed mindset is when you believe that the qualities that you have are determined almost at birth. They're part of you and they don't change. So you might think that you are a science person, and that's your little box that you've made. And it's when you have these little boxes, I just want to point out this definition that you spend your time documenting your intelligence instead of developing it. So how does that affect when we go on in life, right? What happens if there's a challenge in front of you? Well, you might try to get away from that because you have this idea of who you are. And if it's challenging, it can sort of attack your own self-image, right? If you're a science person, but you don't get this science problem, or if you don't get a math problem, instead of understanding that I need to try, or I need to try a different strategy, it's really becomes, this isn't my thing. And we see this a lot in middle school and in girls in particular. There's a big science drop off in this age because they start to encounter some things that are challenging, right? So a growth mindset is like I said, we've been discovering this over the last 40 years or so, but it's the attitude that you can always learn something new and that you learn by your effort. So real quick, let's just do a little exercise. Put in the chat something you can do now that you couldn't do when you were an infant. Say you can think of an infant, tiny, helpless, and now you see some full-grown adults in front of me. What are some things that you can do now that you couldn't do when you were a child? Drive a car. Yes. Oh, and if you don't know where the chat is, it's on that bottom row. It looks like a little comic book phrase, like I'm speaking a thought bubble.
Or even if you want to probably just unmute yourself and say it out loud. I think we have an intimate enough group where we could probably do that.
Yes, it's true.
Ride a horse.
Ride a horse. Yes. Yeah. I mean, a lot of people look at a ballerina and think, wow, they must have practiced this for a long time, but they might not think the same thing of a musician or artist or scientist, right? They think, oh, those people are just natural at this. Yeah. So cook, walk, talk, use a bathroom. Yeah, all of those things are things that we've learned with effort over time. And so when you have this idea of a growth mindset, it really helps the students that you're working with to not see themselves in a box. And the reason why this is important to science identity is that you can, instead of looking at one type of person, which they might think is a white male in a lab coat, anyone can be a scientist if you learn with effort, if you apply new strategies. And for us that are scientists or science teachers, we have the ability to learn and grow as well. Even though science isn't just something that's widely known about in our culture, we still have a lot of I don't know why it says create objects in there. I'm going to see if I can remove that. Anyway, sorry about that. But yes, so we can show that anyone can be a scientist by our possibilities. And what I was just saying is that scientists go to conferences, we go and have peer-reviewed papers, right? And that's kind of the behind the scenes that people don't see all the time. But we are very much growing and learning and failing and getting up and trying again. And it's important to share those ideas with our students as well and the people that we are trying to share science education with. And I wanted to share with you a challenge that I had taking a activity that we did in person and putting it online, just because I know that a lot of you are going through this struggle at the same time. When I used to do this workshop in person, I had little cards that were cut out of different phrases where we would say, oh, this phrase reflects a fixed mindset. This phrase is a growth mindset, and people would sort them according to what they thought. Right? Well, we can't do that right now, but we can do this activity on an online version. And so what I'm going to do is show you a phrase, and we're going to use the poll feature of, hold on just one second. I'm going to go back, right? So you're going to vote in the poll to see if the phrase is growth mindset, fixed mindset, or not sure. I'm going to just bring up the poll. And I'm going to show you the phrase, okay? I wish I was as smart as you are. Is this a growth mindset, a fixed mindset, or you're not sure? So take some time, think about it. I wish I was as smart as you are. Does everyone see the poll?
Yeah, I think that if you're a host or a co-host, you might not be able to participate.
Yes. So Robin, can you can you see the poll?
I could see the poll, and I clicked submit, it disappeared, but it was there.
Okay, I'll relaunch it and see if that helps. Okay, try it now.
I saw the poll and clicked on it and hit submit, and it disappeared also. But I don't see it showing up anywhere else.
Okay. Yeah, to me, it's not showing me any results, any voting. So I don't know.
We're getting 2 votes for fixed mindsets.
Yeah. Okay. So it's a little bit. Yeah, it's only letting Jeff and Ribbon vote, so that's okay. So yeah, this is a fixed mindset phrase because it's saying that you have a fixed quality of smartness. And so rather than being someone who has studied this object, it's just that they're smart, some generic category, right? So here's something different that you can say. I'll try the poll one more time, and if it doesn't work, then we'll just stop it for now. Usually I have someone else launch the polls and just do it that way. So it can be challenging learning astronomy, but if you put in the effort, I know you can improve. So is this a growth mindset, a fixed mindset phrase, or you're not sure? Okay, well, did anybody see that?
Yes.
Okay. So yeah, so this is one way that you can use growth mindset as you are talking with your students or doing the poll. Usually this works. I'm not sure why it isn't right now because, you know, it's, I guess it's Schrodinger's poll, half there and half not. But so I would go through this and talk and have the people vote. And I just want to talk about this idea. A lot of people think that, oh, they got to get away from fixed mindset and not use phrases like "you're so smart." The reason why it's kind of a trap to say you're so smart is because you have to be smart all the time. You can't be learning new things, being challenged by something. You have to know all the answers, and that can be really limiting. Right. Also, all the other students feel bad when they hear you saying that to some people, right? And also it's too vague. So if we want to keep science strong, we have to talk about the process over the praise and say, you know, I see your efforts, I see you trying, and we're, you know, those types of phrases will help your students learn that science is something anyone can do. So saying something like you did, sounds like you did a lot of research. Also, there's this phrase, yet, you can stick that on the end of anything and it makes it growth mindset, right? I'm not good at cooking, but if I put in some effort, I can learn, right? So I could say I'm not good at cooking yet. I'm gonna stop my share here because I know also that we have one, we're running out of time and I want to give Ava some time, but my sort of takeaway message for all of this is that even the phrasing and the ideas that you have about your students' ability can change the way that they think about themselves. A lot of us can go back in our heads and think of, oh, this math teacher really inspired me, or this person who noticed my writing. I really felt strongly about that afterwards. And so if you take the time to see each student, even the one you think is maybe not the brightest light bulb, rather, you know, that they can, if they put in the effort, study and learn these things. And we just got to keep trying new strategies. And the other point I want to say is to try to move away from one type of person, not a science person, an art person, a math person, but people who learn things. We're all learners, and there's not one type of person. So that's my pitch for your young middle schoolers who are learning.
So I'm going to actually take a little bit out of what Brian was talking about and a little bit out of what Teresa's talking about. And I specifically with regards to this age group, they're very unique because middle school, junior high is when I think people form their identities and become independent thinkers a lot more. They want their autonomy, they want their independence, they want to think for themselves. And it's a great time to give them the resources to explain their ideas and explain also their reasoning and their conclusions. And science is a wonderful way to do that. I think a lot of times people assume that you're going to do that in debate or civics. It's wonderful to do it in science because you use deductive reasoning. You get some more objectivity about your conclusions. Brian started off with some images from Mars and from fictional Mars. And this is another really great way to just hook in to these kids at that age, because they are consumers of culture, of pop culture, of science fiction, of comic books, of video games. And a lot of those things have science in them. But do they always have good science in them? So you can take something that they're already interested in, they're already kind of questioning, and bring them in to the classroom with stuff that they're already passionate about. So I am going to do a very quick screen share, and I was going to do annotation, but in the interest of time, and because there's not that many of us, we can just unmute and talk about this image. So, does anyone know what this is automatically when I put it up?
There's the Millennium Falcon. So
Death Star blowing up, I presume.
Yes.
Mhm.
I was trying to think of something that we would all know based on our ages, and that kids now who are anywhere from, 5 or 6 or however old you are when you first start watching this kind of stuff through, 66, 86, whatever. We've got something that people see, and it's kind of an iconic space scene. What I want to ask though is, what do you see in here that might not be accurate, and what might be accurate if this was real, if this was putting on our science hat or natural science hat, accurate or inaccurate?
Probably not the ring around the explosion. There's no other indication where that came from.
Good. Anything else?
the whole fireball, unless there is a lot of hydrogen or something on the Death Star.
Yes, and one other thing that I could not do in a screen share, I thought about playing the clip, but again, too much time to play the scene out, is that there's often a very audible boom in these movies for effect. So this is a thing that is a great starting off point for a discussion with kids, because unfortunately, there is a lot of bad science out there. Now and always. This is something we will be combating as teachers. We want good, accurate science. We want people to take those observations and make the right inferences, not make inferences based on something that your mind sorted away out of a fictional narrative, out of a photograph that somebody doctored up. So we can take that idea that Brian talked about and apply it to something that they are passionate about already, And that might be something you give them some time in the classroom to discuss, you know, what kind of games are you guys playing? What was the last movie you saw? And you take whatever topic you happen to be talking about in science. Whether in this case, I mean, from just this image, you can talk about chemistry, you could talk about physics, you could talk about optics, you can talk about how sound waves travel and what they need in order to do so. And so you're engaging them not only to be good scientists, and you use this opportunity, like Teresa said, there's people who say, well, I'm not really a science person. I'm an artist. I want to go work in Hollywood, or I want to be a photographer, a painter, a musician. And you can apply that. I mean, knowledge is intersectional. So if someone is good at writing, maybe they write a lot of science fiction, but they're intimidated when they're in science class because they're just an English kid. They are going to benefit from being a good scientist, and they may not be an astronomer or an engineer or a mathematician, but they might be a much better writer from their science knowledge. And those are seeds that you plant now. Middle school is a great time to get kids thinking about that, about how their strengths can be applied in all these different fields later. And currently in their lives, because they're having these conversations with their peers, and they have to defend in a good way, good science, and that's being a good citizen as well. So I'm going to go ahead and stop the screen share, and I want to give you guys the last couple of minutes to kind of discuss what we've discussed and add your I see Nancy was talking about her experience. So I'd love for you to, if you have a microphone, Nancy, to talk about that. If not, I could just read what you've written out loud.
Yeah, Nancy put it in the chat.
So I've just unmuted. So I do a lot of my teaching in a planetarium at the University of Washington in Seattle. And I really love using NASA planetary images that are embedded in our software. Worldwide Telescope is free, downloadable. You can use them on your classroom laptops, or projecting in the classroom. And we have an Xbox controller, so when we actually are live together, I can give kids control. And so as a group, we can explore these images, move them around, zoom in and out close, and I'm always asking them, like a scientist, what do you see? How do you think it got that way? And why do you think that? That's
Yeah,
it.
that's
Unless you have
great.
questions for me.
No, I have a planetarium background. Was my primary thrust in my science education. And I love being that you let the kids sort of control the dome. That's an amazing gift that you can do.
The cool thing about Worldwide Telescope is it does have a touring feature, just like Google Earth. So kids can write their own tour. And with our Astronomy 101 classes that local regional high schools can actually participate in, many of our teachers have learned how to operate the planetarium instrumentation. So when they come to a visit, they actually run their own shows, and kids can fly their own tours. And with the Xbox controller, it is a lot of fun. They literally, fly through the universe. Each kid can present their topic that they studied and put together.
That's great. Jeff, you were saying something?
Yeah, I think a lot of times science is taught as a noun, and it's not, it's a verb. And doing science, science isn't this monolithic body of impenetrable granite. You do science. You buy a used car, and you don't take the person's word for it, what condition it's in, and you approach it like a scientist. And most people approach a purchase, even a kid would approach a purchase like a scientist. That's kind of where I would start with that.
I like that. It's kind of it gives meaning to the phrase, we're going to do science now.
Yeah.
Yeah, and I think that it's also very similar to being a journalist. You get those kids who say, well, I'm more of a humanities English kid. the who, what, where, when, and how of journalism is definitely parallel to the scientific method. So you kind of have to make sure that you're turning them back around and saying your strengths there or your strengths here. We're at the top of the hour, so I do want to respect your time, but I'm going to add another quick link into the chat because this YouTube that I found has a really great deconstruction of fictional pop culture science, especially space in movies in the cinema. So it's a really great resource to share with kids if they're interested in those kind of films. And
Can we include these links in the chat to, when we send out the video recording to everyone?
I always put links in later, but if someone wants to grab it now and save it, I want to give them that opportunity. Thank you guys so much for coming. It was always wonderful to kind of bounce these ideas out there, see what kind of feedback we get. And in the coming, years, we don't know how long and what the transition is going to be like with these kind of learnings, whether it's in the classroom or via this sort of platform. We might be doing this a lot more. So please check in to astrosociety.org. And we will be putting up more teacher resources and links to more events like this one that we will be holding. Brian has a teacher institute that will be down the pike. So definitely bookmark us or save our links so that you could get more resources from us.
Yeah, we have a series called Educators at Home at ASP. So feel free to sign up for the newsletter. I know some of you did already, but yeah, it's just at astrosociety.org. We can maybe stop the recording now, and if there are people who have questions, we can discuss that